Let's go over some examples. We will do one example for each electron domain geometry. First, we draw the Lewis structure. Remember to follow your 5 steps. BeCl2 is an electron-deficient molecule, so it ends up with only 4 electrons around the central beryllium atom. Second, count the electron domains on the central atom. Beryllium has 2 single bonds and no lone pairs, so it has 2 domains. Third, draw the ground state orbital diagram for the central atom, which in this case is beryllium. Beryllium has 4 total electrons, but only 2 of them are valence electrons. We have left the 2 electrons in the 1s orbital out of this diagram because core electrons are not involved in hybridization. Maximize the unpaired electrons by moving paired electrons out of lower energy orbitals into higher energy orbitals. In this case, we take an electron out of the 2s and put it into an empty 2p orbital. There is an energy cost associated with this, but it gets made up for when the atom bonds. We've made an excited state version of beryllium, so we put an asterisk next to the Be symbol. Before doing this step, beryllium would not have been able to make any bonds because it didn't have any unpaired electrons. Now it has 2 unpaired electrons, so it can make 2 bonds, 1 to each chlorine. The problem is that the 2 single bonds in BeCl2 are exactly the same as each other. This would not be the case if one was made with an s orbital from the beryllium and the other was made with a p orbital from the beryllium. That is why hybridization is still needed, not just promotion of an electron. Next, we create the hybrid orbitals using our magic number, our number of domains. BeCl2 has 2 domains, so we take 2 atomic orbitals and combine them together to make 2 hybrid orbitals. We're always going to work our way from lowest energy to highest energy when combining orbitals. So we take our lowest, which is s, and our second lowest, which is p, and combine them together. We call the resulting hybrid orbitals sp hybrid orbitals because they are made from an s and a p atomic orbital. These new sp orbitals have a medium energy that is higher than s and lower than p because their energies basically got averaged. As we place the electrons in the hybrid orbitals, we follow Hund's rule, since the hybrid orbitals are all the same energy as each other. That means we put the electrons in unpaired, which allows each hybrid orbital to make a bond to 1 chlorine. Although we ended up hybridizing the orbitals that had the electrons, it is not the presence of electrons that tells us to hybridize a particular orbital. It is only the number of electron domains that tells us which orbitals can become hybridized. Here's what hybridization looks like pictorially. A spherical s orbital mixes with a dumbbell-shaped p orbital to make 2 new hybrid orbitals that each have the same shape and energy as each other. They're just pointing in opposite directions. Each hybrid orbital has a little lobe and a big lobe. We will mostly focus on the big lobe in the pictures that show multiple hybrid orbitals all together. Although 2 sp hybrid orbitals end up looking a lot like a p orbital, they are different in an important way. Since the p orbital is a single orbital, it can only make 1 bond. It could bond either on its right side or its left side, but not both. A p orbital would not be able to give BeCl2 its linear geometry. Having 2 sp hybrid orbitals, on the other hand, allows 2 bonds to be formed and gives BeCl2 its linear geometry. Let's look at another example, BH3. We draw its Lewis structure. Again, it is electron deficient, so the boron only has 6 electrons around it. We count the number of electron domains on the boron. It has 3 single bonds, so 3 electron domains. We draw the ground state orbital diagram of boron. Boron has 3 valence electrons which go into our orbital diagram. 2 go into the 2s and 1 goes into a 2p orbital. We maximize the unpaired electrons by taking an electron out of the 2s and putting it into an empty 2p orbital. This creates an excited state diagram for the boron. Now there are 3 unpaired electrons, which allows us to make 3 bonds to the hydrogens. We use our magic number, the number of domains, which in this case is 3. We take 3 atomic orbitals from the boron and hybridize them to make 3 new hybrid orbitals. We call them sp2 hybrid orbitals because we used a single s orbital and 2 p orbitals. The superscript tells how many of each orbital was used in the making of the hybrid orbitals. The sp2 hybrid orbitals all have the same energy as each other, which is why we draw them side by side. Their energy is lower than p, but higher than s. Each ends up with 1 unpaired electron, so each sp2 hybrid orbital can bond to 1 hydrogen. Here's what sp2 hybridization looks like pictorially. A spherical s orbital mixes with 2 dumbbell-shaped p orbitals to make 3 new hybrid orbitals that each have a large lobe and a small lobe. They end up pointing in 3 different directions and make the characteristic 120-degree angles and trigonal planar electron domain geometry. Because we always combine orbitals in the same order, if we know the electron domain geometry, we also know the hybridization. For example, 3 domains is always going to be sp2 hybridization. All 3 of the molecules on this slide have 3 domains around the central atom, and therefore all have sp2 hybridization. The first molecule has a single bond, a lone pair, and a double bond, so that is 3 domains. The middle molecule has 2 single bonds and 1 double bond, so that is 3 domains. For the third molecule, we can focus on 1 carbon at a time. Each carbon has 2 single bonds and 1 double bond, so that is 3 domains. As a hint, the sum of the superscripts on the hybrid orbitals should equal the number of domains. For sp2 hybridization, the superscript on s is an understood 1, and the superscript on p is 2. 1 plus 2 is 3. This is a great way to check your answers. How many p orbitals are required to generate a set of sp2 hybrid orbitals? Is it A1, B2, C3, or D4? The correct answer is B, 2. I've been a little tricky here, asking you this question right after telling you to add up all the superscripts, but you need to pay attention to what the question is asking. This question is specifically asking about the p orbitals, so we would just look at the superscript on the p. If we want to know how many total orbitals of any type are needed, we would add up all the superscripts. Let's look at an example which will have sp3 hybridization. We draw the Lewis structure of CH4. We count its electron domains. It has 4 single bonds, so 4 domains on the carbon. We draw the ground state orbital diagram of the central atom, which is carbon. Remember to follow Hund's rule. The 2 electrons in the p orbitals go in unpaired because the p orbitals are the same energy as each other. Although we have some unpaired electrons, we don't have enough to make the 4 bonds, so we still need to maximize the unpaired electrons. We move an electron out of the 2s and into the empty 2p orbital. We use our magic number to combine atomic orbitals to make hybrid orbitals. We combine an s orbital together with 3 p orbitals to make 4 sp3 hybrid orbitals that are all the same energy as each other. They each end up with an unpaired electron, so they can make the 4 bonds to the hydrogens. Here's what it looks like pictorially. A spherical s orbital combines with 3 dumbbell-shaped p orbitals to make 4 new sp3 hybrid orbitals that all have a large lobe and a small lobe. They are pointing in the characteristic directions to make a tetrahedral electron domain geometry.